We're doing our calculus AB notes for 3 Riemann sums and definite integrals. So thinking back to what we did the last couple of days, so if I go to the rectangles, we were drawing these Riemann sums. So we were taking this area under a curve and we were approximating it by using rectangles, okay? And so n was how many times we were dividing this up. And we were going from an interval on this one from 0 to 4. So we could think of that as from A to B. And then n was how we were dividing that out. So like on this particular one, our delta x, how wide our rectangles was, we got by doing 4 minus 0 and then dividing by 4. So that was like the width of each of those intervals. And we had 4 of them. So what we're looking at now is we're looking at n increasing, the number of subintervals increasing. So instead of just doing 4, maybe we do like 100 or something. So as we increase n, the length of the largest subinterval is going to approach 0. So as we get more and more of those intervals, they get tinier and tinier until even the biggest one is going to approach 0. Prior to now, our f of x was assumed to be continuous and non-negative. It did not lie below the x-axis. So we haven't worried about that at all. We will today. The length of the largest subinterval of a partition, delta, is the norm. And we use this like double lines around delta symbol for that of the partition. If every partition is equal in length, then we get our delta x by doing b minus a over n. That's what I just showed you. Furthermore, as that norm approaches 0, means that the number of those little subintervals that we have is approaching infinity. And that's kind of like the first one, just worded differently. So this is all about still finding that area, looking at those sums. So this brings us to the definite integral. So definite integral is from a to b of f of x dx, we're going to say. And a is our lower limit or lower bound. And b is our upper limit or our upper bound. And remember this f of x dx, that's like our derivative. And so when we take this antiderivative, that's what we're doing here with this integral, right? We're taking an antiderivative. This represents the value that the antiderivative is changing from a to b. So this is over that interval from a to b. So this represents the value the antiderivative changes on the interval from a to b. So if a function f is continuous on that closed interval, then f is integrable. So that just means like because it's continuous, then I can go ahead and integrate it. So that's what we're looking at there. I think I need to make this go out just a tiny bit and maybe adjust it a little bit. Much better. Okay, so a definite integral is a number and it can be positive, negative, or 0. For a definite integral to represent an area, then it needs to be continuous and non-negative. So if it's an area specifically, if they say find the area, then we can't have negatives. If they're just saying find the integral, then it is going to be, then it could be positive, negative, or 0. So sometimes this is area, sometimes it's going to be the integral, but this is a definite integral and also sometimes an area as long as it's not positive. So we're going to start by playing around with areas of a bunch of different things. So I'm going to start by sketching. We're kind of doing what we did in 4.2 for now. Only we're looking at finding real areas. They're going to be a little bit easier. So this is saying we're looking at this function, or I guess it's really a derivative, right? 4dx, and we're looking at this from 1 to 3. So I'm going to look at this 4, and I'm going to graph y equals 4. So y equals 4 would be a constant. So here's 4. And I want to find this definite integral from 1 to 3. So this is on the interval 1 to 3. That's what that's really saying. So here's 1, 2, 3. Here's 3 over here. And what it's saying is I want to find the area underneath this curve, only it's not a curve, it's just a line, from 1 to 3. So I'm looking at this area right here. So I don't need to approximate this with a bunch of rectangles. And I don't even need calculus to figure this out. It is just a rectangle. So what I'm going to do here is I'm going to think about how my height on my rectangle is 4 and my width is 2, or base is 2. And all I'm going to do is multiply 4 times 2 and get 8. So let's remember here that our derivative, we're looking at f of x equaling 4. And then we're looking at our f, capital F, like our antiderivative would really be like a 4x plus c. Okay, so we want to be thinking about what's going on here because this says 4 dx and I'm integrating that. This would be like the thing I already have. This is like my derivative, and then this one would be like my antiderivative. So just kind of keeping that in mind as we work through this. Mostly today we're just looking at a bunch of pictures and we're finding area. So we've got numbers here today. We're not trying to practice our integration rules. We're just finding a bunch of areas. So on the next one, we're looking at the function x plus 2. So y equals x plus 2 is what I want to graph. And if I think about graphing y equals x plus 2, it starts at 2 and it has a slope of 1. So there's my function. And I want this from 0 to 3. So here's 0, 1, 2, 3. And I've got a different kind of shape this time. So before I had a rectangle, it was pretty easy. This one I've got a trapezoid. So to review the area of a trapezoid, it is going to be 1/2 the height times base 1 plus base 2. And base 1 and base 2, these guys are parallel. Bases are parallel. So really, it's like I'm finding it on its side, right? This is one base, this is the other base, and this would be considered my height. But it's okay. We don't need to turn our paper. We're in calculus. We can kind of envision that. So let's look. I've got 2 on this side. I'm not sure what this side is, but I could try counting it out, or I could look at it in my function. If I put 3 in here, 3 plus 2 makes 5. So this would be 5. And this would be a height of 3. So I'm going to end up with 1/2 times 3 times, let's see, 2 plus 5. So let's see, that's 1/2 times 3 times 7, which is going to be 21 halves. And again, this is my derivative here. And then if I think about the antiderivative, right, I would have to integrate that. And I'd have to make it an x squared over 2 plus 2x plus c. So always kind of be thinking about that because that's going to be our next step. So if this is that derivative, then my antiderivative would be x squared over 2 plus 2x plus c. So don't forget about how those work. All right, on the next one, I'm asked to find this integral from -2 to 2. So what do I need to do there? I need to look at this function and figure out how to graph it, and I'm just not sure. So sometimes what helps is to set it equal to y and kind of solve it and change the way it looks. I'm going to erase that ugly 4. I don't like it. So if I think about squaring both of these sides, I'd have, that's not a whole lot better, a y squared equals 4 minus x squared, and then I'm going to move the x squared over on the same side as y squared, and I have a circle. So if I think about working backwards through this and solving for y, I didn't have a plus or minus root. I just have a positive root. And so what that means is this is going to be the upper half of a circle. And it's going to have a radius of, let's see, square root of 4 is 2. And because I just have x squared and y squared, my center is 0, 0. So a little bit of review here. So let's go ahead and draw that. So from 2 to -2, because my radius is 2, it's going to go up to 2 here. That's actually a pretty good looking half circle. Radius is 2. So if I'm going to find this integral, if I'm going to figure that out, remember I can just think of it as area here. So area of a circle is pi r squared. So this is going to be 1/2 pi r squared. And my radius is 2. So I've got 1/2 pi times 2 squared, which is going to be 2 pi. And that's a fine answer. I don't need to do anything else to that. Last one's a little bit tricky. So let's go ahead and graph 2x. So let's see, 2x is going to go through the origin, up 2 over 1. Okay. But the problem is this says from -2 to 1. So here's 1, here's -2. So I'm looking at this area here. So what we have to remember on this one is that this area is going to be positive because it is above my x-axis, and this area is going to be negative. So let's see if we can kind of see why that is. So if I am looking at finding the area of this, or I keep saying area, and I don't really mean that, do I? Because we want to have a negative here. And if we were just looking at area, we would say it's positive. So when we're finding this definite integral from -2 to 1, we're figuring out like between this graph of that function and the x-axis. Like that's the shaded region that we're finding. So this one over here is a triangle. We've got a 1/2 base times height thing going on here. And if I think about how this functions up 2 over 1, then this is going to be a -4. This is going to be a 2. And I kind of slipped that negative right in there, didn't I? And that's because we're going down from that x-axis. So it's like I have a negative height here. So if I think about 1/2 base times height here, well, I'm going to have a 1/2 times a base of 2 times a height of -4. So that's how I get that negative. I keep thinking area, but I know it's not really area, but we are finding the area of a triangle. And then I'm going to add this one over here. So plus, and this is going to be a 1/2. My base is 1 this time, and my height is 2. So 1 and 2. So let's see what we come up with. So 1/2 times 2 times -4 is just a -4. 1/2 times 1 times 2 is just going to be a +1. And so we end up with a -3 on this one. So if they had said find the area of 2x from -1 to 2, and they gave you like an interval or something, and they specifically asked us for area, then we would have just taken the absolute value of this part of it and made it 4 plus 1. But they didn't say that. It just says find the definite integral. So that kind of leads us into what happens when the function is not positive on the entire interval. Well, when it's positive for some x values and negative for others, then it's the sum of the areas above the x-axis counted positively and the areas below the x-axis counted negatively. So just exactly like what we did. So here's some different properties of integrals that we're going to kind of play around with. And some of them will make sense. Like this first one is saying if I want to start at A and end at A, and I'm looking at f of x dx, well, what happens? What would be that area? And I'm really finding a definite integral, but it helps for me to think of area. Well, if I'm starting and stopping at the same point, I haven't really accumulated any area because I haven't moved at all. So the start and end is the same, which means I just have a 0 here for my area. Okay, so this next one is maybe a little bit surprising. If I'm moving from A to B, and again, I'm assuming that on my graph here, like here's an A, here's a B, so I have an A less than B. So if I'm going from A to B, if I want to go backwards from B to A, then I just have to change my sign and make it negative. So I'm going to write equals negative of the integral from b to a of f of x dx. So if we go forward, we start with the small, we go towards the big, everything's normal, it's good. But if I want to go the other way around, if I want to start at b and go left towards a, then that's going to put a negative. It's going to be opposite. So just something to keep in mind as we work through these. From a to c of f of x dx, so this is assuming that b is going to be between a and c on this one. Then what I could do is I could break this into two parts, and I could say, well, we could use the integral from a to b of f of x dx, and I can add the integral from b to c of f of x dx, which kind of makes sense, right? So if I am looking at a big, and I'm going to go back to area again, under a curve all the way from a to c, well, I could find this little part, and then I could find this little part, and I could just add them together. So that's all that we're getting at there. On this one, if I have a constant being multiplied, just like we've done with limits and everything else, I can put the constant and multiply that in front of the integral. And we call these definite because we have numbers here again or letters here again. And then on the last one, if I have, and we've already kind of done this, but not with a lower and upper limit here, not with definite integrals. But if I look at two functions being added or subtracted, well, I can just break that apart. And like I said, we did do that before, but not without these bounds. So we can break them apart. Okay, so if f is integral and non-negative on the closed interval from a to b, then 0 is going to be less than or equal to the integral from a to b of f of x dx. So basically, if f is integrable and non-negative, then the integral is also non-negative. So if my function is non-negative, then basically my integral is also non-negative. Non-negative. Two ends there. I'm kind of off the page. Sorry about that. I hope that hasn't been an issue for a while. There's everything we had down before, just in case I'm getting close. There's no way I'm doing this over again. If f and g are integrable on the closed interval from a to b, and f of x is less than or equal to g of x for every x in the interval from a to b, then, and this is a closed interval, I guess I should be saying closed every single time, then if this one is less than this one, then the integral of a to b of f of x dx is also going to be less than or equal to the integral from a to b of g of x dx. So if the functions, if we have one function less than or equal to the other one, then the integral will also be less than or equal to the other one. So we're going to play around using some of those properties up above. So we have this integral from 1 to 3 of negative x squared plus 4x minus 3 dx. And we want to evaluate it, but we have just these little pieces. I know what x squared is. I know what x is, and I know what just this dx part is by itself. So let's see what we can do with this. So I'm going to take this integral from 1 to 3 of negative x squared plus 4x minus 3 dx, and I'm going to think about how I could break this apart, right? So I could take each part of this polynomial and I could break it apart. So I could make this the integral from 1 to 3 of negative x squared dx, and I could have the integral from 1 to 3 of 4x dx, and I could have, I guess I'd write minus the integral from 1 to 3 of 3 dx. But this isn't quite right still, is it? So I really need just an x squared by itself. Well, I could think of this negative as like a constant that I can put in front. So I could put a negative out here and have from 1 to 3 of x squared dx. And then here I really want an x dx, but I have a 4 in front. So I'm going to put the 4 in front as a constant. And I could think of the 3 as a constant also because I just want my dx to be by itself. So minus 3 times the integral from 1 to 3 dx. So let's go ahead and make our substitutions now. So for this one right here, I know that's going to be equal to 26 thirds. So that's going to give me negative 26 thirds plus, and then I have 4 times this integral here, and I know that integral is equal to 4. So plus 4 times 4 minus, and then over here I have 3 times this integral, which I know is equal to 2. So minus 3 times 2. So I'm just making these substitutions. So negative 26 thirds plus 16 minus 6. So I really learned instead of getting a common denominator at once, do as much as you can and then get a common denominator. So I'm going to go ahead and combine these two. And then I do want to get a common denominator here, multiply top and bottom by 30. So this would be 30 thirds, and that gives me 4 thirds. And I have a note over here. I have no idea why I wrote this, but I'm going to just share it now. I think I'm doing number 9 for you so that you can figure out the other ones. They're saying the limit. Here's our norm as that approaches 0. So that makes sense, right? We're talking about the width of those intervals getting super, super small and approaching 0. And then we've got summation notation or sigma notation from I equals 1 to n. And this is 3c sub, this has got to be an I. Nope, it's a 1 plus 10 delta xi. And this is from -1 to 5. This must just be the original problem. Again, I have no idea. I just have this random note that I'm supposed to do this problem, and I've not looked at it. So write as a definite integral. So what I need to do is this is going to become my bounds, so -1 to 5. And then instead of having this part and thinking about subbing an I don't even know, C sub 1. I would have to look at that. I'm kind of wondering if I wrote down the problem wrong. But what I have for this part is I have 3x plus 10. And then instead of that delta x sub I, remember we're thinking about dx instead. And hopefully remember back from differentials when we said like as delta x got smaller and smaller and smaller, it was basically just like a dx. So that's what we're doing. So this is how we would write that one as a definite integral. Hopefully it will be enough to look at that pattern and figure out the rest of them in the homework. So good luck on your homework. Please ask questions in class, and hopefully we will see each other soon.